last class we were discussing the basic configuration for the operational amplifier, and we saw how it is made up of 3 stages: input stage, intermediate stage and output stage. Now, coming to specific op amps, popular op amps, we would like to see almost all components of this particular op amp. So, obviously 741, 747, these are the operational amplifiers which are general purpose operational amplifiers available. Almost every manufacturer makes this, okay, configuration similar to this. So, let us see how the various minor details regarding protection, compensation, biasing, etc., are taken care of by this configuration. Let us quickly identify here the input stage, okay, in white color. Obviously, the input stage we have decided to use NPN current sink as the active load, okay, to the input stage. So, you can see this active load here, okay. This is the same block that I had discussed with the current amplifier put there, so that the current reflection here is exact, okay. So, this is nothing but the current mirror active load using NPN structures. Now, in our earlier basic configuration we had not put any of these resistors. Now, note that we have put resistances in the emitters, okay. It is not really serving the purpose of making the currents equal. Currents were more equal before the resistances came into existence, because the resistor ratio is not all that, okay, better matched than the geometries themselves, okay. But we are intentionally putting resistive degeneration. One purpose is automatically served, that is output impedance is increased for the, but that is a minor purpose for which it is put. The major purpose for which these resistances are put is for offset compensation. Let us now discuss this. If these resistances are equal, because of the transistor mismatch, these two currents will be unequal. If these two currents are unequal, okay, even when the input signal is 0, okay, there will be an input current into the next stage. If there is an input current to the next stage, automatically DC current that we are talking of, output is going to saturation, right. So, in order to reduce the output offset, one technique is of compensation is to make these two become unequal in a direction such as to compensate for the mismatch. Is this clear? So, I am now introducing two unequal resistances here, R1 and R2, okay, to make the output offset go to 0. That is why this is an easy technique of compensation. Now, how do I do it? The manufacturer puts equal resistors, then he brings out these two terminals and mentions these as offset compensation terminals. One has to put a potential divider between these two, and the center tap one will connect it to minus Vs. So, what happens if it is center tap, then equal resistances will be across this. It is deviating from the center tap, okay, center position, the tap, if it is deviating from the center position, then we will be generating unequal resistance. Depending upon the kind of offset, you can either increase this resistance related to this or decrease it related to this just by using a pot here. So, this is externally connected component okay, which is nothing but a potentiometer with the center tap connected to minus Vs, that is all. So, this kind of compensation is available in certain 741s, where these terminals are brought out. If these terminals are not brought out, you cannot compensate for it, obviously. Right. So, in certain packages you will find these terminals are in fact brought out. Okay. So, then compensation can be easily done using this procedure. Is this understood? This is one thing special about it. So, we will remove this, because this being an outside component, we should not clutter this already complicated circuit with all this. In case of therefore offset compensation, we need this potential meter. Now, this is nothing but the bleeding resistance we are talking of, okay, in order to make this transistor operate sufficiently high current, okay, so as to prevent the beta fall off. Okay. So, this portion is understood thoroughly. This is connected to plus Vs. Now, this structure here, let us understand. We said if we have decided to use NPN current mirrors, we must drive it by means of PNP pair, but we do not have good PNP pair. So, what do? We now use a cascading of NPN with PNP. So, in such a manner, now you can see, as far as signal is concerned, okay, the base current of this is NPN base current. So, emitter current is going to be definitely beta times that. So, the effect of input impedance etc. is going to be retained, okay, because of good beta. This current is going to be the same as emitter current of this structure, and this is strictly speaking, okay, base is connected to ground, let us say. Therefore, this is a common base structure for signal, right. So, you can see here that by using this structure, I have got almost a PNP like looking structure with high beta. Okay. So, this is the trick that has been played in 741 input stage in order to get PNP like performance using a combination of NPN and PNP structure. So, that is taken care of. So, input impedance is going to be 4 RE, okay, 2 RE of this and 2 RE of this. REs are going to be the same because operating currents are the same, into beta plus 1, where beta is that of NPN, right. So, no problem. Is this clear? Now, one thing has to be emphasized here, that this base current has to flow somewhere, because both of these will have a base current flowing like this, right, finite base current, okay, because betas of these are not going to be too high, right, this is going to be pretty low. So, this current, substantial current, is now going to flow through this, okay, and of course, through this. This is a current mirror in the reverse, right. So, it will sense the current, total current here, which is the bias current actually, and feed it here, and this current is fed back to this. Yeah, I think now you can see there is some change, mistake. This is the low valued current mirror, with we have to now put a resistance in the emitter. So, this is the low valued current that is generated. That low value of current, okay, is used in generating the feedback currents. These are the two feedback currents. This is the base current, okay, and this is the total collector current getting reflected here. So, that means the emitter current of the whole thing is getting fixed by feedback now. Okay. So, this current shall become equal to this plus this, which will determine the operating input current of the input stage. Is it clear or not? So, let us say this is I dash, then this is going to be I dash. Okay. So, these two currents will be I dash by 2 and I dash by 2, right. So, these two currents are I dash by 2. So, these two base currents will be I dash by 2 beta P and P, right, same thing, I dash by 2 beta P and P. So, what will be this current? This current will be I dash by beta P and P. So, I dash by beta P and P, which is considerable, plus I dash shall become equal to I. Okay. So, I dash by beta P and P plus I dash is equal to I. Is this clear or not? So, you can see that the bias current of the input stage is fixed in a pretty complicated way compared to the conventional scheme of straightforward current mirror biasing. The mirror reflected current is made equal to the fed back current, which is equal to the emitter current of the operating transistors, right. So, for the given configuration, please find out for the values of resistors etc., assuming supply voltage VSS and minus VSS, okay, as let us say 12 volts, please find out the value of the operating current I dash. Beta P and P, you can assume it to be something like 10. Okay. So, you will get the value of that. So, compared to this, you can see how simple the structure was for the one that we discussed in the last class. Right. That means, if bipolar transistors of good PNP were available, good BNP transistors were available, we could have straight away gone for the conventional biasing scheme instead of adopting all this roundabout way of biasing. Okay. Next, this is the reference current, okay. Vs minus Vs, that means 2 Vs minus 2 V gamma divided by this R is the bias current, okay, reference bias current, which will bias all the stages in this. Right. So, the ratio of these two currents, okay, is the one that is going to be now made very high. This divided by this is made very high. So, that this current is made current of the order of microamperes using a resistance of the order of tens of kilo ohms. So, this portion of the circuit, is it clear? Okay. Coming to the intermediate structure, obviously we have 2 V gamma here, V gamma, 2 V gamma here, and we are putting Darlington pair here. Okay. So, the input stage impedance also is boosted up by the Darlington pair. Not only that, this potential is maintained at the same potential as this, so that the current reflection is good. Okay. Early effect is not coming into picture. Now, here forget about these transistors, these are coming only as protection transistors, later we will discuss this. This is the compensating capacitor. This portion of it is nothing but what we had discussed in the earlier lecture on not current mirror, this is voltage reference, which can generate a voltage which is nothing but V gamma into 1 plus R2 over R1 necessary for biasing a class B in class AB mode of operation. Okay. So, this R2 over R1 is made less than 1, so that the voltage between these two is equivalent to slightly less than 2 diode drop. This block also we had discussed. Okay. So, this gets automatically biased by this current source, okay, and therefore, the Zener voltage here is going to be less than 2 V gamma, necessary to bias the class B in class C AB mode. So, this is understood. This is the active load, which is straightforward, there is not much of a difference, and this is the output stage. These resistors are current sense resistors for protecting the output stage. Output stage, as we see, is nothing but again PNP NPN combination, okay, and you can see the straightforward protection which is necessary for any output stage that we had learnt in voltage regulator being still used here. This transistor normally is off, primarily because this voltage is not good enough to bias it in the forward direction. So, this is the sense resistance or sense. The moment a current which is I into R sense develops a voltage V gamma, this transistor gets into the active region, okay, diverts the additional drive that otherwise would have increased the output current, resulting in the output transistor getting destroyed. Okay. So, this prevention of additional current drive which otherwise would have increased the output current is prevented by this transistor which is already put inside. So, typical value of that resistance is given how much? 26 ohms. If you consider that 0.6 divided by let us say 25 ohms, okay, is going to be how much is it? About 14 milliamperes, right? 24 milliamperes, right. So, it is typically of the order of 20 milliamperes, that is the order of current, short circuit protection current, that is coming here in the case of 741s. That means, you must never connect any load. Now, this is important. You might just connect a resistance like 1K, right, and expect 10 volts to be developed. Okay, say 10 volts 1K, so 10 milliamperes safe. But what matters normally is that suppose it is capacitive load, okay, you are totally unaware that you are having a capacitance at the output, and for the signal frequency which is pretty high, the current increases beyond 24 milliamps. You are not able to notice it because you have put a resistance, okay, which is quite tolerably high enough, so that this current limit is, but the capacitive load will keep drawing more and more current at high frequency, and the waveform gets distorted now because it goes to the current mode of operation. Okay. So, at certain signal current waveform gets distorted, okay, because of this current limitation coming into picture. Okay. This is something that you have to again notice. It is similar to our slew rate limitation, right. So, please always keep a check on all these limitations coming about because of protection circuitry, etc., etc. Okay. Now, why didn't exactly similar structure be put here? Obvious. If I had to put exactly similar diversion scheme here, I should use PNP, and PNP is not an efficient structure to divert traffic, because while diverting the traffic, right, the amount of current drawn from this is extremely small. Okay. So, in such a situation, what we do is, I do not have to divert the traffic at maybe near Spencer's. Okay. I can start diverting the traffic near Egmore feeder lines to central itself. There is no need, because I know that most of the lines are coming to central, right. I do not have to start diverting the traffic exactly around central, if there is traffic blockage into the Mount Road. So, same thing is adopted here. I do not have to divert the traffic for this here. I will do it. Where did it come from? I am asking. This traffic, where is it coming from? Obviously, this is coming directly from, when I drive a current into this, there is going to be current in this direction. If this current exceeds, this current correspondingly exceeds, right. It has nothing to do with these current sources. Okay. So, the source of traffic here is going to be from here. Okay. So, it is enough if I divert the traffic here itself. Okay. So, I put a good NPN transistor and a sense resistance here, you can see, and that is going to remove the current drive into this the moment I think that this current is going to exceed a certain limit. Okay. This current is going to exceed a certain limit, the beta of the transistor is low. So, this current is going to be pretty high, and therefore, it is this transistor which you are now trying to protect. This current is going to be of the same order of magnitude as this current. Okay. So, you are trying to protect this. So, imagine that you are trying to protect this and thereby protect this also. Now, you might say, why did we put this resistance here? Okay. For the AC, when it is not coming into picture, still it should act as a symmetric structure somewhat. Okay. So, this resistance has been put there. Right. So, this kind of current short circuit current protection scheme is adopted in most of these op amps. Yeah, values are different. It is, we are not very sure, because now this is beta dependent, right. Okay. So, this value is different from this. Okay. So, as long as it is offering some short circuit protection, it is protecting the output transistor, right. The rating for this transistor is totally different from this transistor, right. The current capability of this transistor and these are different. Okay. So, that is why these values are all different. Okay. That is that the designer has put, after lot of tests and finding out variations, possible variations of beta over the widest range of temperatures, etc., has put the suitable values here. Okay. Now, the gain of the intermediate stage is affected because of that. Correct. That is a point I forgot to point out. The gain of the stage is obviously getting affected here, but you just look, because the resistance is put here, okay, the impedance level has gone up here. Okay. So, actually gain is not going to get much affected, okay, because of this kind of scheme, right. The impedance level here has gone up further, so that means the gain of this stage has gone up by some amount. Okay. So, anyway, this is a low valued resistance here, okay, that is about 50 ohms, okay, and this resistance is of the order of hundreds of kilo ohms. So, the gain of this stage itself is now hundreds of kilo ohms by 50 ohms roughly. So, what is it equal to? It is not 50 ohms, it is 50 plus Re of this transistor, right. Let us say if the transistor is operating at 1 milliampere current, okay, then it is 25. So, 75 ohms. So, the gain of this stage is straight away, okay, hundreds of kilo ohms by 75 ohms. So, it is more than, okay, about 10 to the power 3 to 10 to the power 4. So, 10 to the power 3 to 10 to the power 4 gain is got by this itself. Okay. So, then about gain of about say 100 to 50 to 100 is got by this particular stage. So, overall gain is about 10 to the power 5 to 10 to the power 6. So, that is the kind of gain that you have for this stage. Okay. So, now that we know practical op amp, how its performance factors are fixed, what are the internal parameters which are to be chosen properly in order to design the op amp for a given specification, etc. We will discuss a variation of an op amp which is called comparator. Now, there is always a tendency to use operational amplifiers which are used for negative feedback application as comparators. Obviously, this is not good practice, okay, because when the application is comparison of voltages and there is not likely to be any negative feedback, we have already understood that there is no problem of frequency instability arising, and therefore, there is no need to compensate. And if we do not compensate, we have the widest possible bandwidth of usage. So, a good sense always is, if the application is for comparison of voltages, then we must not use internally compensated op amps at all. We must go either for externally compensated op amps and we do not put the compensating capacitor, or we must go for comparators which have been designed with the application of comparison in mind. Okay. Network wise, obviously both are high gain amplifiers, but there is a lot of difference in the actual design of a comparator as well as operational amplifier. So, that is why we want to highlight the difference in design between comparators and op amps. What is a comparator? Again, comparator is a high gain amplifier, because in order to compare one voltage with reference voltage accurately, the difference in voltage that is necessary to change the state from high to low should be as small as possible. This is achieved only by making the gain equal to infinity. So, that means a good comparator is automatically a good high gain amplifier or op amp, but its large signal properties we are interested, because it is primarily used either at its low level or at its high level. It is intended for use as an interface circuit between maybe analog world and digital world, okay, where the digital world is facing only two levels, high and low. So, a comparator therefore has to be designed specifically catering to the digital world as the output and analog world as the input. Okay. So, in such a situation we have to bear in mind, okay, these different worlds which the comparator is seeing. First of all, the output level need not be plus Vs and minus Vs. It need to be compatible with the logic family to which it is going to be connected. Let us say it is TTL, then it should be 5 volts and 0 volts. Okay. When this comparator 710, 711 became popular, TTL circuits were in great use in almost all digital designs. Okay. And therefore, this was designed with output level becoming totally compatible with that of TTL logic family. So, that is as far as the output is concerned. The input is still the differential amplifier stage, no doubt, like in the case of conventional op amp. But once again its responsibility is different. Voltage, two voltages it is comparing, and even though it is ultimately going to be in the output is going to be in the high state or low state, it has to go from high to low or low to high, and this has to occur at the highest possible speed now of operation. Now, we are not bothered about slew rate etc. for this, right. Slew rate is the characteristic of the structure when output is following input to a certain extent and the distortion starts happening, because now output can no longer rise at that rate. Whereas here, okay, we are not bothered about output input relationship at all. We want the output to reach high as quickly as possible, whether it is a linear relationship or a nonlinear relationship, we are not bothered about that. Okay. So, speed is what is important. So, the comparator property when we discuss, we will not talk of slew rate or gain bandwidth product etc., we will rather talk of rise time and fall time. Okay. How quickly it can rise from low to high and high to low. So, this is what is talked of, and that has to be made as small as possible. Again, the parameters that make it small will be the same parameter, these are time constants, because it is when the structure is in the active region that it is going from high to low or low to high, and therefore, the time constants have to be made very low. Straight away capacitors are not to be used at all, compensating capacitors should be avoided altogether. Okay. Then resistors have to be made as low as possible, and therefore, we very rarely use active loads in comparators. Okay. We use physical resistances of the order of, you can see, hundreds of ohms. Now, you might say the gain is going to be pretty low. One thing, operating current is not going to be low, right. Operating current is going to be pretty high compared to the conventional op amp, right. So, straightforward current mirror technique has been adopted to obtain currents of the order of maybe milliamperes. Apart from that, the resistances are low. So, the gain of this stage is going to be very low. That need not be a botheration as far as you are concerned, because we can adopt positive feedback in order to boost up the gain here. Now, this is an important point. Nowhere in application of amplifiers we use positive feedback, because it is highly sensitive. Gain becomes then more sensitive to active parameters than before. But here we do not bother about sensitivity. Okay. It is not likely to stay as active mode for long, it is going to quickly go through that. During that time, okay, gain has to be kept as high as possible. The specific value of gain is not going to matter. So, you will see that positive feedback is used in order to boost up the gain. What is positive feedback? If you have a gain of 100 for the stage, 1 minus, let us say this is now going to be 1 minus, okay, let us say 100, okay, into let us say 200, 1 by 200. So, what will be the gain now? This is A by 1 minus A into beta. Amount of positive feedback is 1 by 200, okay, very small. So, I have been able to make the gain now go to 200, double the gain by using little bit of positive feedback. Now, that is what is done. This is a differential output stage. Let us carefully look at it. This input stage is feeding on to the next stage. What is the next stage? This structure? It is? What kind of amplifier is it? Huh? It is not differential, it is common emitter amplifier, just as in the case of other op amps. So, the next stage, even though it is drawn like, okay, there is no current source here, this is voltage source, level shifter, right. The collector potential here has to be higher than that here, right. The collector potential here has to be higher than that of the base. So, level shifting voltage of 6.2 volts Zener is used, okay. But for AC purposes this is ground, and therefore these two are two independent amplifiers, okay. One is connected to one collector and another is connected to other collector, and therefore you are likely to lose gain by a factor of 2, because these are two independent stages, but I do not want to lose it. So, what is done is this output is getting amplified here, okay, and this output is sensed here by the common collector stage here and fed to this. So, what happens now? For one of the structures, okay, there is positive feedback, for the other one there is negative, because there is a phase difference of 180 degree between these two. So, for one there is positive feedback, for the other there is negative feedback. We want for the one that is going to be fed to this stage positive feedback to occur. So, you can check the input from here to here, there is no feedback, there is no phase shift, okay. There is a phase shift of 180 degree here, no phase shift here. So, from here to here there is a phase shift of 180 degree, there is no phase shift here. So, that is positive feedback for this. I would like you to replace this structure by the equivalent circuit and prove that the gain is exactly behaving like this. If the initial gain is 100, okay, the final gain is 100 divided by 1 minus 100 into 1 over 200, and it becomes twice the. This is another technique of converting differential output to single ended output by giving positive feedback, adopted primarily in comparator circuits where positive feedback is not going to matter, okay. In fact, you might say that in comparator ultimately one might use it with total positive feedback. That means, it is instead of 1 over 200 we will make it 1 over 100 itself and make the gain equal to infinity. That is called, if the gain of the amplifier now, even though it is finite, okay, I have been able to make use of positive feedback and boost up the gain to infinity. This is regenerative feedback, or it becomes a Schmidt trigger, right. If you make this more than, okay, 1 over 100, then there is considerable amount of positive feedback, and it can never remain in the active region. It will either go from high to low or low to high on its own without signal being necessary to push it, okay. So, it becomes that. So, we know that gain is not very important in the case of comparators primarily, okay, and therefore, we live with low gain in order to boost up the speed of operation and then give positive feedback here in order to increase the gain to the original value restored. Now, from here it is connected to again common collector output stage. This is of course biased properly, and there is a level shifting arrangement here 6.2 volts once again, okay. You can check this, this is 6.2 volts. If this transistor is driven to saturation, it is likely to happen, this voltage is going to be 6.2 volts and V gamma, okay, this is 6.2 volts. So, this is going to be very nearly the ground potential, okay. If this is off, okay, then this is likely to go up to VCC, and that is prevented by what is called as what? Clamping circuit here. This diode is not going to conduct if this is going to be in the active region, you can see, because these are identical stages, 1.1 k plus 2.8 is 3.9. So, the voltage between this and this is going to be 0. Therefore, this is going to be reverse bias most of the time, okay, when it is in the active region. So, this diode is not in picture, but the moment this goes off and this is pulled up to VCC, this potential is rising very fast up to VCC, and it is clamped down to a certain DC potential which is less than VCC. So, that the output potential is which is a range within the high range, right. It should be less than 5 volts, greater than maybe 2.5 volts. So, anywhere between 2.5 to 5 volts. That is, for all the supply voltage ranges, it should lie within this range of 2.5 to 5 volts. Okay. So, this clamping structure is for that purpose. Okay. The output level obviously depends upon the supply voltage you are using, what it is exactly. Okay. So, I would like you to therefore find out for this structure as a homework problem the high state as well as the low state. That simply goes by saying that this transistor is either in saturation or in cutoff mode. Okay. So, please do analyze the whole thing and find out the total gain of this stage. The gain is coming because of two effects. One is it is 500 divided by 2 RE, okay, into 2 because of the positive feedback. Therefore, it is 500 by RE into 3.9 K by RE of this thing. How do you find out the operating current of this? It is very simple. You can find out the operating current of this, okay, and this structure, right, all these things, and this potential, okay, is going to be the same as this potential, and you know this potential here. How do you know? This is 6.2, this is 0.6, you know the drop here, this is 0.6. So, you know the potential here. So, you know the operating current here. You have to come in an indirect fashion here to find out the operating current of these are common emitter amplifiers. Okay. So, the operating current is fixed because of this, right, potential getting fixed here. So, this current is known, and therefore, this current should be same as this current. Okay. So, you know the gain of this stage, which is 3.9 K divided by RE of this transistor. Okay. So, overall gain is that gain into this gain. So, this comparator is one of the most popular comparators, which is good for most of the interface applications, high speed interface applications, okay, that is in DTA converters, okay, and function generators, all such circuits you can use this comparator very well.
Sir, but even if you use negative feedback in this, it's going to behave as a linear device.
Yes, but what will be the danger of negative feedback here? It will start oscillating. You can see that also. Even without negative feedback, if your power supply itself is not bypassed properly, you will see that apart from high and low, you will have a thick line on the top and bottom here. Why? Because it is still used in open loop, and it has all the poles coming into picture, and the feedback is coming through the power supply. Okay. Therefore, you have to, whenever you use comparators in a practical circuit and also in open loop, you have to be extremely careful about power supply lines also. Okay. So, this cannot be used in negative feedback. This can be used in positive feedback mode without any problem, but not in negative feedback. No, none of the comparators. If you have to use, then you will put a what? Compensating capacitor between this and this and this. In fact, there are two separate feedback paths here, right? There is an internal feedback here, okay, and here, right? So, it might cause problems, right? Most of the times, the internal feedback itself is sufficient, because please remember, this collector based capacitor is there. We are putting additionally some capacitor to make it dominant, so as to make it work for every gain that you are thinking of. but when it is under open loop, if it oscillates, okay, the amount of capacitor that you have to put here may be extremely small, or it is not oscillating because this capacitor is already coming as dominant pole, because that is the Miller effect capacitor. So, do not assume that there is no dominant pole here, okay. That may be quite dominant enough, okay, under this open loop situation, even if there is small amount of negative feedback, okay, not to cause any oscillation.
Is too small here.
Where? Yes, we are not bothered about that.
For that stage, second stage.
For this stage, input impedance, this is 500 ohms. Okay, so if you it is operated at let us say 1 milliampere current or so, is about 25 ohms, okay, into beta 200, so about 5 kilo ohms. So it is not loading it at all. This input impedance is of the order of 5 kilo ohms also, and it is 500 ohms here, okay. So it is not loading.